So again, thank you so much for that really kind introduction. And in general, I've been taking part, of course, unfortunately, remotely the whole semester at the deep learning program taking place at INI. So it's really been a great experience. And it's too bad we can't do this in person, but I really want to kudos everybody involved in setting things up so well online and giving us a chance to interact even remotely. So with that, I'll begin just wishing health to everyone. Unfortunately, we've been seeing the numbers rising again. So I really want to wish everyone health, especially with the holidays coming up, and hopefully we'll be able to meet soon again in person. So with that, let me begin. So I think, the title of this workshop is really, really exciting, and I'm looking forward to hearing a lot of the talks. The part that I'm going to try to focus on today is more related to the first word, the interpretability. And in particular, we've been trying to promote a framework that we've been working on. And of course, many other people are contributing to this framework and working on various ideas related to it. What we refer to as model-based deep learning. So trying to kind of incorporate models into deep networks. And here particularly, we're going to look at applications to communications and imaging, but of course, we could think of much broader applications in many different areas. So as everyone here, I think, knows, deep learning is, of course, everywhere nowadays. It leads to huge success in many different applications, and primarily in problems that were traditionally difficult to tackle using conventional methods. So I think probably two of the leading applications where deep learning has really had an impact is speech processing, speech translation, and computer vision, which are areas where really modeling is quite difficult. And here really we've had the most impact. So of course, on the one hand, we could do amazing things, things that have a lot of value, things that are maybe, interesting, but not really clear what the value is, like spawning faces if you really want to. But of course, we could do a lot of things that have a lot of value, like getting, really, really substantial classification rates and things that humans, far superior to anything a human can do. But on the other hand, this of course comes with a cost. So we know that we have to have very large training sets to get this good performance. Interpretability is really a key issue, and we work a lot in our lab on biomedical applications, medical imaging, and there interpretability is everything. So it's very hard to be diagnosed by a machine that is not telling you why you're getting the particular diagnosis. So that has been a main issue. The training could be computationally very exhaustive, again, especially when we need very large training sets and we're playing around with a lot of parameters. Other really key issues are robustness, generalization, right? So we may do well on our particular training set, but it's not clear how well we're going to do when we see new data. And again, I keep on going back to medical imaging because that's an area where we're working on a lot. And there, these issues, of course, are very key, right? If I trained on patients with one diagnosis without knowing, and then I come with, unfortunately, some unique case, then, I don't want to be diagnosed by a machine that doesn't know what to do with something that's different than their training set. And finally, complexity is becoming more and more of an issue. So, for example, if we look at GPT-3 that, leads to amazing translation abilities, it relies on 175 billion parameters. So again, that's good for applications where they're machine driven. But if you're thinking again of going to a doctor and being diagnosed by a machine with billions of parameters, obviously it's very hard to get credibility given to, or explainability given to that result. Now, if we look for a minute at the other extreme of what we did traditionally in signal processing and communication networks. So here, traditionally we relied very heavily on models. So, any standard signal processing and communication problem typically begins with a model. We model the input-output relation between the data that we have and the underlying parameters we're interested in. It's relatively easy to incorporate domain knowledge because we have this nice modeling. We could incorporate structure we have in the problem, for example, via regularization. Typically, we could get inference from relatively small amounts of data. And the nice thing is that we also have, an arsenal of analytical techniques to assess the quality of the output that we obtain. So these are some of the advantages of kind of more traditional signal and communication processing. However, two of the key points here is that we really require accurate model knowledge. So if we don't know the model, then obviously this framework kind of falls apart. And the other issue is that the inference, even if we could set it up as a nice optimization problem, it could end up being very difficult and very slow. So these are two of the drawbacks with kind of more traditional signal and communication processing. So what we'd like to do, and like I said, obviously there's many people working on these types of ideas. So what we'd like to do is try to see if we could take the best of both worlds. So, traditional deep learning is kind of throwing away everything we know about the model, about the structure, et cetera, and saying, you could replace all of that by a black box. But what we're saying is we don't want to replace all of that by a black box. We want to only replace the parts that we have to replace. So the question is, how can we do this in a systematic fashion? So let me just as inspiration take, probably one of the most basic problems in communication, which is symbol detection. So this is really, the most basic task in a communication receiver. And in the setup, you have a transmitter that's transmitting information, symbols to a receiver. And the difficulty is that, in between, you're going to have a channel, which is going to typically distort the signal in a known or unknown way. So you're going to be sending some symbols S, and at the receiver, you're going to get different symbols Y, which are, of course, a noisy version of S. And if it's a more elaborate channel, then you'll have fading and other effects as well. And if you want to go ahead and then recover the symbols from the data Y, the standard thing to do is to assume a model. And the most popular model that's still being used in systems today is this very basic linear Gaussian model. So you're going to assume that your data Y is related to your underlying symbols S through some, linear model, which you typically assume that is known, or you estimate and then assume that it's known. And you'll typically assume that you have some Gaussian noise. So if you assume this simple model, you could go ahead and come up with an optimal symbol detector. And of course, you can use different optimality criteria. So you can try to maximize the likelihood or maximum posteriori detection if you know the prior, et cetera. And that will give you the optimal detector. So this is kind of the basic way communication problems are set up. And of course, the advantages is very simple. We have an optimal receiver, but some of the difficulty is that, first of all, it relies on a very simple underlying channel, which is okay for simple channels. But as we're moving forward to 5G and 6G and looking at more elaborate channels, at IoT channels where things change very rapidly, we have a lot of interference, then this simple linear Gaussian model may no longer capture well the characteristics of the channel. The other problem is that obviously we don't know the channel, even in the simplifying model. So we typically just rely on estimating the channel. Okay, so we repeatedly send pilot symbols and estimate the channel. But again, if we have many, many users and things vary very rapidly, then that's not going to be very practical. So this is how we are forced to move from these simple underlying principles governing communication to more elaborate channel models. So how could we do that? Well, the standard thing to do, just like people do in any other field today, is to say, okay, let's forget about all of this, just replace all of it by a black box and do end-to-end learning. So, we could either really send over the channel or simulate different channels and send as many symbols as we want, get received data, take our favorite learned network and train it to do symbol detection. So there's been a lot of work along these lines. We'll mention some of it later on. But the difficulty is that, first of all, this requires very large training sets in order to get good results, especially if the number of symbols grows very large, so it becomes combinatorial. It's very, very difficult to implement this in practice. So if you're thinking of learning on the edge, if you think of an IoT setting where channels are changing, but everything is done in a distributed network, this is not going to be very practical to keep on retraining on the edge with very low power devices. And from a more theoretical point of view, at least, something that has been driving a lot of the work that we've been looking at in our group is that, when things are known, we expect to get the optimal solution. Whereas when you're using deep networks, you never really have control over what you're getting. So even if the environment happens to become more friendly and you could estimate the channel, you have no way of kind of plugging that in and getting the optimal result. So ideally, we'd like algorithms that, are not so intensive, could work on the edge, could adapt very rapidly to changes. But maybe most importantly, when things are ideal or known or we can estimate them, we do want to approach the well-established methods that we know are optimal. So just as an example, again, if we look at a very simple detection problem over a marker channel, then one of the most popular decoders is, of course, the well-known Viterbi decoder. We'll get to it later on. And the Viterbi decoder is optimal under certain conditions that we just mentioned briefly before. So if you look at just deep networks that have been developed for these types of problems, even when the channel is known, they're not going to be doing very well. On the other hand, if we look at model-based methods that we're going to discuss later on, the beauty is that they're going to do well when we don't know the channel. And when we do know the channel, they will get back to the optimal performance. So this is maybe to give some inspiration to what we're going to be talking about today, is kind of trying to move gradually between the model-based methods and deep networks, but in a way that we preserve interpretability, preserve explainability as much as we can, don't need a lot of training data, and reduce to the known optimal solutions when the systems become more known and more controllable. So that kind of summarizes and hopefully gives some motivation to what we want to show today. And the next question is, of course, how could we do that? So, to answer that again, still on a high level before jumping into the details, let me try to give kind of a bird's eye view of, model-based signal processing or optimization-based signal processing versus deep networks. And this is obviously an oversimplification, but hopefully will be helpful to illustrate what we're going to be doing. So in the standard optimization-based signal processing setting, again, you're going to have your input, what you measure, we're going to call it here Y, and there's the desired output. So these are the parameters that you're interested in, which we're denoting here by X. And you're going to assume that you have a model. So you're going to assume a priori that Y is some known function of X. So here we're denoting it by Y is equal to approximately G of X. And then since, of course, you don't have equality, when you're given Y, you want to optimize some metric. So let's say the squared error difference between Y and G of X in order to be able to estimate your unknown parameters. So you could, easily write this down as an optimization problem and use your favorite optimization solver. So just as an example, you could use, let's say, a projected gradient method. And typically you'll end up getting something like this. So you'll have some pre-processing. You'll then have the iterative part of the method, which again, typically you could break up to some generic computation and then something that depends on the model, which you may not know. And this is the part you're going to iterate. So you're going to go through these steps several times, and then you'll end by some post-processing, by some mathematical operation at the end. So, very roughly speaking, this is how an optimization problem is going to look. Now, on the other hand, if you look at deep networks, or deep learning, then of course, the whole setup is entirely different. So you don't assume you have a model. Instead, you assume that you have many, many, many paired inputs and outputs. This is your training data. You have a pre-existing network that you're going to be using. Okay, so it doesn't depend on your model. You chose, for example, a Usenet, a UNet, a ResNet, whatever you chose. And now what you're going to do is you're going to learn the weights in this network from your training data. And when the new input comes in, you're going to put it through your network and hope that you end up getting something that is close to your true output. Okay, so these are very, very different paradigms. And the question is, how do we integrate them? So in this talk today, we're going to focus on two methods. The first is what's known as unfolding and unrolling, which has become very, very popular in recent years in the signal and communication literature. So we'll talk a little bit about that. And there we're basically integrating these model-based algorithms into the framework of a deep network. And then we'll look at an idea that's a little bit the reverse, where we're going to start with the algorithm itself and integrate a deep network into the algorithm itself. So let me just very briefly show what these two ideas mean, and then we'll kind of go through them more systematically. So unfolding is a beautiful idea that goes back to the original paper of Gregor and Lacoon from over a decade ago, but I guess originally didn't receive so much attention, and in recent years has been getting more and more attention and many, many, many different extensions, both on the algorithmic side and on the theory side. And the idea is to start from the iterative algorithm. So this is kind of the iterative algorithm we've shown before. And what we're going to do is we're going to explicitly write out several iterations of our algorithm. So we're going to assume, let's say we take 10 steps. So we choose, a small fixed number. We're not going to take thousands of iterations. So we write down 10 steps of the algorithm. And at this point, we didn't do anything. It's still just an iterative algorithm. But then in the final point, what we're going to do is these iterative steps, as we stated before, actually depend on certain model parameters, which we may not know. So in the final step, what we're going to do is we're going to free those parameters. So by freeing those parameters, I mean we learn them from data instead of assuming that they're known and fixed in advance. So this is going to end up giving us a deep network, which is not so deep. Typically, it's actually pretty shallow, which is one of the advantages. And the structure that it has is not a predefined structure, but rather a structure that depends on the original optimization problem that we started with, and of course, the choice of optimization solver. So we get a deep network, but it has the flavor of the underlying optimization problem, and we have the freedom to choose which parameters we're learning depending on what we know and what we don't know. And of course, in the extreme where everything is known, we're just back to solving our underlying optimization problem. So this is the underlying idea in unfolding. We'll talk more about that as we go through the talk, but those of you interested, we have a recent review we wrote on this method that's kind of very, very high level with many different applications. So those of you interested could go ahead and take a look and see more details. The other approach we're going to look is kind of the opposite approach. So in unfolding, we start with the underlying formulation and kind of derive the algorithm. There's many applications, and we use this particularly in communications, where we have a good algorithm, we have a good solver, and it's not necessarily a direct solution to an optimization problem, but it could even be just a good heuristic. So an example is the Viterbi decoder. The Viterbi decoder is a dynamic programming approach on some original optimization problem, but it's not directly linked to an optimization solver. So in that case, we're going to actually start with the algorithm itself. So you could think of, just writing down, and we'll show this later on, the Viterbi algorithm, and just looking at what parts in that algorithm depend on the model. So instead of replacing everything with an end-to-end network, we're only going to look at that particular block that depends on something we don't know, and only replace that block by a shallow network. So we're not doing end-to-end learning, but only learning what we have to learn. And this looks like a very trivial idea, and it really is a trivial idea, but it wasn't popular or used. The more popular thing was to do end-to-end learning. And the beauty is that we can show that this is very effective in practice, and it also approaches optimal performance under many different scenarios. So those of you interested in this approach, we've used it primarily in communications, and we also have a review focused on the applications in communication networks. So that kind of summarizes, where we're headed, what are the two approaches that we're going to take, and then from this point on, it's really more going into applications and details. So more specifically, what I'm going to do in the rest of the time is look first at applications of unfolding in different imaging applications. We'll talk about just generic sparse recovery to set the stage, and then move on to ultrasound, super resolution in optics and ultrasound. And then depending on time, we'll talk about the second approach, primarily focusing on communication networks and seeing how we could get, different types of communication decoders for different types of channels using that underlying approach. So I know you said that there's questions at the end, but if it's possible, I'm super happy to take questions as we go through as well. So if anybody has questions, feel free to kind of unmute and just shoot ahead. I'm really happy to answer questions. All right, so let me start by just making a little bit more clear, hopefully, what unfolding is. And we'll start with the basic example that dates back to the original paper, which talked about sparse recovery. So in a nutshell, as we said, we're going to take our underlying iteration, just explicitly write it out several times, and then allow each layer to have parameters that we don't assume are fixed, but rather we learn them from training data. So if we look at particularly at the very well-known sparse recovery problem, this will lead to what's known as the LISTA network, which was the first kind of unfolded network that was proposed in that original paper by Gregor and LeCun. So the underlying sparse recovery problem goes back to this very simple linear model where we assume that the noise is Gaussian, but we also assume that we have a sparsity prior on X. So we're going to incorporate that by looking at an L1 regularizer. And then if you just use your favorite proximal gradient solver to solve this problem, you're going to get the well-known ISTA method, iterative shrinkage at thresholding. And again, it's just a proximal gradient method. So you take a gradient step and then project it onto the constraint set, or a proximal projection onto the constraint set. And what that ends up looking like is this is the gradient step. So you have a step size and linear steps that depend on the matrix A, which are just implementing the gradient. And then the thresholding, the projection, ends up being a soft thresholding. So this is what one iteration looks like. And then what you do to develop the unfolded network, or the learned ISTA network, is you write this down k times. And now you have some freedom. So in the original paper, they wrote this down k times and then learned these blocks from data. What is more popular to do nowadays is to free all of the blocks so we don't tie them, meaning we don't enforce them to be the same in each layer, but rather we allow them to be different in each layer. And you could play around with this. You could assume that they're different. You could tie them and assume that they're the same. You could ignore the known relationship between these two blocks and just learn them as separate linear networks. You could assume that there is a relationship between them. So you see here already that it's a combination of art and science. So, the science part is coming from the optimization problem. The art part is which parameters you end up freeing, which you keep fixed. And a lot of this depends, of course, on what you know about the problem, what structure you want to incorporate from the problem, and of course, the availability of training data. So, the less training data you have, the fewer parameters you would typically want to be able to learn. But all in all, if you use this framework, regardless of how you play around with it, what has been observed over and over again, and we'll shortly see a variety of examples, is that it ends up leading, first of all, to methods that don't have a lot of parameters. These networks are not very deep, so they're very data efficient. They have low complexity and memory footprint. And what has been observed is that they learn fast. They tend to generalize very well. They tend to be quite robust. So even when you plug in data that is quite far from your training data, you tend to get very good results. And of course, they're interpretable just by construction because they're based on the underlying optimization. And also another nice thing is that as more data becomes available to you, also data, but more knowledge becomes available to you, it's easy to incorporate it into this framework because, again, the deep network is just a result of an optimization problem. So when you modify the optimization problem, and we'll tell you how to modify the underlying network, and we'll see some examples for that later on as well. Okay, so hopefully the underlying idea is clear. And again, if it's not, please feel free to ask questions. So if there's no questions, then I'm going to move on and start showing some applications in imaging and in ultrasound. So the first application that we originally looked at was together with a group of Vishal Monga. And
I think because you so kindly said it was okay for people to ask questions, just so you know, unfortunately, given the way we had to set this up, it's not possible for.
Oh, sorry. I'm sorry. Okay, sorry.
No need to apologize at all. No. But we have got some quick, very relevant questions. Maybe I'll just read them out. So.
Oh, sure.
So one question is it always possible to introduce the model in this way, or when are there situations where this doesn't work well?
Yeah, a really, really good question. So I hope by the end of the talk, I convince you that that it should always be possible. And of course, there's different layers of incorporating a model. So the part I'm talking about right now, which is very optimization driven, is obviously relevant when you could set up an optimization problem. And that is not always the case. So, that's why we also looked at alternative methods. The second method I showed, which starts from an algorithm, is always possible because there's always some underlying method that people used until now, right? So I always tell my students, think of what people did 5 years ago. So what did you do to solve this problem before they were deep networks? And, that's always a starting point. So, that's another way that you could address this. And finally, the third thing I'm going to show later on, and I'll mention it now because it's relevant to this question, if it's a totally new problem. So for example, we've looked recently at, detecting COVID, which is a new problem. So that doesn't fit any of the categories. There's no optimization problem. There's no what did people do 5 years ago, because this problem did not exist 5 years ago. And this is something real we've been working on with hospitals in Israel. And there actually the training set is a huge problem because we don't have large training sets because it's whatever for privacy reasons, whatever, it's very complicated to collect this data. So we don't have large training sets, and robustness, of course, is key. So there we still incorporated models by using things that doctors refer to as models. So just as an example, at the end, COVID is a lung disease, right? So for example, doctors know very well to segment the lungs. It's not necessarily directly related to COVID, but obviously knowing where the lungs are should be informative to the deep network. So that's an example of a model that we incorporated within this model-based framework that is not based on anything systematic. It's not an optimization framework. It's not an algorithm that people used before, but still having this mindset that I can incorporate models by thinking of how I would do it in signal processing. We were able to incorporate it into the network, and it really boosts performance almost by 10%, which is quite substantial. So I would say, I'm saying this with caution because saying something could always be done, of course, you can't really prove, but at least I would say we have not yet encountered something where, we couldn't use this methodology. How far you could take the methodology, of course, depends on the problem, but the more people work on it, and the more particularly we can establish theory showing that this works, more people will use it and it will become more convincing. So, we've been recently doing a lot of work with Miguel. So thanks a lot, Miguel, on trying to, figure out a lot of the theory of these ideas. And I'm talking about that less today because it's work in progress. But I think the more we also establish the theory and the analytical results, the more, I think people will feel comfortable using these types of ideas.
Fantastic. Thank you. One other very, very quick question is, what's the typical range of K that people use?
So K being the number of layers, I guess?
Yes.
Yeah, so I would say typically we don't use more than 10. So, in our work, most of the networks we use were 10 and below. So it is really very small.
Thank you. We got a few other great questions, but I think I'm going to hold those to let you continue.
Okay, good. But hopefully it gave people, some pause. Okay, great. So one of the first applications we looked at together with Professor Vishal Monga is actually a very standard deblurring problem. And to be honest, at least from my point of view, when we started looking at this, I was looking at more as a benchmark, like, could I use something very, very simple without doing something fancy and achieve close to what people do with more elaborate networks. And what you'll see is that we actually were able to get better performance than what people do with very elaborate networks. And I think it's really nice to see how, and even something super generic where there's been, literally thousands of papers, still by doing something very principled, you could quite easily get very good results. So what is the problem? So the problem is, we have an image, it's blurred by an unknown kernel, and we have random noise. And, we're given the blurred image and we want to recover the underlying image. So there's many methods to solve this problem. What we're going to look at here is, doing a total variation in the gradient domain. So more specifically, you could set up an optimization problem where you say, okay, I want to find the underlying unknown kernel and I want to find features. So instead of looking for the signal, we're looking for features of the signal that best match the signal and filtered versions of the signal. So the reason that we allow filtered versions is because we want to match, let's say, the signal and its gradients, not just the signal itself. And then we're going to add an L1 prior on the features and just a bounded norm prior on the unknown blur. Okay, so this is quite standard from an optimization point of view. And then, we go ahead, we use our favorite solver, particularly here, we use the variable splitting approach because it's quite convenient due to the formulation. And, you end up just getting an underlying optimization problem. You could use the optimization problem, it gives reasonable results, but of course you're going to do it by unfolding it and learning from training data. So that was the next thing we did. So we just unfolded it, learned from training data. And here, because this is a problem that so many people looked at, we just looked at the same types of examples and the same training set that people looked at the literature. And the nice thing is that using this approach, which we refer to here as DUBLID, we actually got better performance than, the methods that the most recent methods that were reported in the literature. And again, the network is very simple, very lightweight, and very interpretable. I just told you what we did, right? It's only gradient based. So all the code here is available online, and you could go ahead and look at the results and play around with the code as well. So, that was very motivating because it says that even a problem that people have used very elaborate methods for, we could get very good results by just following basic optimization principles. So the next thing to address, though, is that in what I showed before, we basically assumed a regularizer, right? We assumed, let's say in that case, an L1 norm on the feature. And that works in images because we know that L1 norms work quite well in images, or at least in particular classes of images, but that may not be true for all imaging problems. And of course, it's not necessarily true when you move beyond these basic deblurring problems. So the next question that we wanted to look at, and this is work done together with Professor Ruud van Sloan and Danielle Friedman from Google, was, could we also learn the prior? Now, of course, there's many methods to learn the prior. That's one of the most popular things today in deep learning, right? There's GANs and invertible flows and many, many things people do to learn priors. But the difference here is that I don't want to learn it offline, like people do in GANs and in other techniques, but rather I want to unfold the prior as well. So what we do is it's the exact same philosophy, but instead of assuming a known norm, we use a learned way to learn the prior. So here in particular, we're using invertible flows, and I'll explain why in a minute. And then we unfold the invertible flow together with unfolding the underlying optimization problem. And the reason why in here in particular we use invertible flows is just because they have the nice property, of course, that they're easily differentiable. So then when I unfold them, the learning becomes very simple. Okay, so instead of assuming that the PDF is fixed and learned in advance, we learn it together with learning the underlying optimization problem. So it just essentially the regularizer is replaced by a parameterized PDF, and we learn the parameters of the PDF and the parameters of the optimization problem together as we're unfolding. So it's a very simple idea, but by using invertible flows, just from a practical perspective, it becomes relatively easy to implement. And in this case, I'm not assuming that I have a known regularizer. So again, if I have a reasonable regularizer in the problem, I should use it. But if I don't, then we can use this to regularize as well. And this already allows me to solve more difficult problems. So these are, again, examples that we looked at from known databases, where here we're looking at much more difficult problem where we had, very strong corruption, either by this type of noise, which is not, your typical Gaussian noise, or by just having areas in the image that were totally deleted. And in this case, by adding this invertible flow, we were able to get really good results. Again, much better results than competing methods that are much more elaborate. And we're still preserving this interpretability as well as we go through the network. So, that's kind of the basic idea, together with learning the flow, together with learning the regularizer. We could extend this in many ways. So just to give one example, again, I don't want to bore you with many details, but I think this is, at least for us, this was kind of a nice example, and it allows us to move to higher dimensions as well. So here we're already looking at images, and this is a separation problem. So particularly this problem is in ultrasound, where we want to view the blood flow, but you get very strong clutter from the tissue. And you could think of a similar problem when you're looking at radar, for example, where you have very strong background clutter. So here the goal was to try and separate the blood flow from the tissue. And typically this is done with SVD methods. So, or principal component analysis, but it's just not good enough to do the separation in this case. So what we looked at here is starting again from an optimization framework where we looked at a robust PCA formulation. So we modeled the data as being low rank plus sparse. And then again, we unfolded the method to get a deep, robust PCA method. So again, I'm going to show just the high level ideas, but those of you interested, we've done a lot of work and model-based learning in the context of ultrasound. And those of you interested, we have a review dedicated particularly to ultrasound imaging. So just as an anecdote, we worked on this method before COVID, before Corona in 2018, and we called this method Corona. It then stood for Convolutional Robust Principal Component Analysis. And I have been getting funny emails about it in the past year or so, but this was done before COVID. So just bad choice of name. But anyway, okay, so what does this look like? So, we have our data. We write it as a sum of low rank plus of tissue background plus blood, where the tissue background is modeled as low rank. So we have a low rank regularizer, and the blood is modeled as sparse. So we have a sparse regularizer. And again, we use our favorite proximal gradient method. And if you just write down the proximal gradient, you'll end up getting an iterative algorithm that has kind of two branches. In one branch, you have linear transforms and thresholding on the singular values. And in another branch, you have linear transforms and thresholding on just standard soft thresholding that we saw before. So this, for example, is a type of architecture that you wouldn't see in a standard deep network. Okay, so it has like these two branches, these two different nonlinearities. So you see already that it could lead to very interesting networks that are not the standard things that people do. And then, of course, we unfold it, we learn the linear transforms from the data, and this actually gives very, very good separation, as you can see over here. So it really, really nicely separates the background tissue from the blood. And this particular network was trained on two sets of images. So two different mice. From each one, we had 10 images, but obviously that's a really, really small training set. And it worked very well. We actually used the train network even on ultrasound images taken from humans. So, obviously it generalizes very well, at least practically.
Ina, can I just interrupt briefly with a couple of great questions that have come in that I think will be really helpful to, if you don't mind, just addressing them.
Sure.
So the first one is from Sarah. I'll read out her question. Is there a relationship between the learned ISTA and Bayesian deep learning? Though the problem formulations are definitely different, we usually think about Bayesian learning as the natural way of incorporating prior knowledge in DNN. Did we compare the two approaches in terms of generalizability and robustness, or can you comment on the difference between these different ways of updating priors?
Yeah, so that's a really good question. So I guess, when you say Bayesian deep learning, it can mean so many things. So I guess the question is, exactly what are we comparing? But I think the main thing, and I hope I'm capturing correctly what you mean by Bayesian deep learning, but I think the main thing is that in what we're doing, we're actually, the architecture itself, the network itself is incorporating the structure. So it's not that we have something fixed and we're changing, the external metric, or we're adding a regularizer to the metric that we're using for learning. We're actually changing the architecture itself. It's incorporated into the architecture. So I think that's, that's a very fundamental difference between the two.
I guess one thing that people may be wondering about is when you talk about learning the parameters in different parts of the network, potentially you could have some uncertainty in those, be modeling a distribution over those parameters. Is that something which people do?
Yeah, so that's, again, all of these are really, really good points. So first of all, let me just say that a lot of this is work in progress. So I think, there's many ways to extend this. But in terms of, trying to address that maybe more directly. So, one way to incorporate that is that if I have some distribution about the parameters, I can add that as a regularizer, and that again will affect the network. So, I have a slide that shows some work that I was doing with Miguel on, robustifying, let's say, the Lista network. And in some sense, that captures that, not in a Bayesian setting, in a more deterministic setting of adding uncertainty, but you could do it at a Bayesian setting as well. So if you could think of, if I have a Bayesian prior, I could look at a map metric rather than, a least squares or maximum likelihood metric, and that would incorporate that uncertainty and then unfold that metric. So the difference, though, that I want to emphasize again, and that relates to my previous answer, is that it's not an external metric for doing the learning. It's the metric that drives the structure of the network. So when I change that very first metric, when I add either a Bayesian prior or just deterministic uncertainty to it, it's going to actually change the architecture of the network. Now, of course, I could also add it to the external learning metric outside, like you do, let's say, in Bayesian learning, but I could do both. So I could add it outside on the external metric, but also inside on the metric that's deriving the architecture. And then the novelty would be that the architecture itself has components in it that are related to that uncertainty.
Perfect. We have another popular question from Renee Vidal, who actually gave a Turing lecture earlier this year, but I think that so he's asking about what exactly is the approach by which you are handling the unrolling and the training, but I think you've addressed that. Apologies if not, please upvote that question some more and we'll come back to it. But I think Yonina's done a good job of addressing that. Sorry for the interruption.
Okay, great.
Thank you.
No. I enjoyed it, and I think if I'm sure if these questions are coming up, then it's good for everyone to pause and get some answers. Okay, great. So I showed one example in ultrasound. We could do this in many ways, so I'll go this quite quickly, just to kind of flash it out there. So one of the things that are very basic in ultrasound and in radar is beamforming, and of course people use this a lot in communication as well. And here we could do the same thing. So we could do a model-based adaptive beamforming where we learn the adaptation weights from the data. So again, we don't replace the whole structure by a deep network, but rather we learn only the weights in the beamforming in a, from training data. And as you can see over here, this leads to really good performance. So first of all, the nice thing is that the computational cost is very low. It's still a simple beamforming operation, but because the weights are learned, we get much better contrast and much better resolution. And in a sense, it's almost for free because the complexity is the same. Here, the training was done from a single patient, I should say, not a single image, because each patient has many images. But in that sense, it's kind of like self-supervision, right? Because I'm not training in advance. It's done from that very same patient. Okay, so you could think of more and more examples, but hopefully everybody gets the idea. I do want to mention, and this is what I mentioned before, is that even when we don't have an optimization algorithm, we could still try to do the same thing of incorporating the knowledge we have. And this is an approach we've used recently for COVID detection. So when COVID started, again, at Weizmann, I had a big biomedical engineering center, and we have many doctors that we work with, and we had several meetings to try to understand kind of, what are the needs that we could help. Of course, there were many needs that unfortunately we can't help with. And one of the things that came up was quick detection. So people come to the emergency room, you don't want to start putting them through, taking them through the different wards, and how quickly could you just detect that they have COVID or not? And we looked at both X-ray and ultrasound. And this was a very complicated problem. Actually, it sounds like a simple detection problem, but the training data is so diverse, and there's different machines and different users and patients, some are standing and some are sitting, and everything that the books tell you not to do is the data that we got. It's totally corrupted. No one has any clue of what's going on. Many errors, and nobody has the patience to tell us, what is good and what's not good, et cetera, et cetera. So here, incorporating knowledge was very, very important. But on the other hand, there's not a lot of knowledge to incorporate. So here we used a lot of knowledge about the physiology. So, the lungs, right? Like we could think of having, oh my gosh, I am so sorry about that. So I'm at home and that's the front doorbell. I do apologize about that. Hopefully somebody will get it at some point. So sorry. Oh, good, sorry. So I turn off the phone, and that's like the one thing I don't even think there's a way of turning that off. Anyway, going back to our talk. So for example, we added segmentation masks and incorporated them, as regularizers. And, those were things that really, really helped a lot. So just as an example, even in cases that are not principled or not coming from an optimization problem, we could kind of take the same methodology and in a little bit more sloppy fashion, of course, incorporate it even into simple classification problems. And we did the same thing in ultrasound. So this is work done together with Professor Libertero Demi from Italy, where they used ultrasound a lot. So they had a good data set that we could use. And here again, there's a lot of knowledge that doctors have about B lines and plural lines. I don't want to go too much here into these details, but these are things that doctors know, again, about lungs in general, and we were able to incorporate them to really boost the performance. So that's an example where even though we don't have an optimization problem, we could still use this notion of regularizers to change the architecture, again, not as an external learning metric, but to actually change the underlying architecture. So I'm just going to keep track of time. Yeah, okay. So let me move on and show, I'll try to go through this quickly, some applications that I think are interesting to a totally different problem of super resolution. So one of the basic problems in optical imaging is super resolution, because we're limited by Abba's diffraction limit, which says that we can see details that are smaller than half the wavelength that we're using for illumination. So for example, if we're using an optical microscope, we can see bacteria, cells, but we won't be able to see proteins and small molecules, which is of course, what you'd like to see today. So in 2014, the Nobel Prize in Chemistry went to this really, really clever idea of optical fluorescence microscopy, where the idea was to introduce fluorophores into whatever it is that we want to image and control the fluorescence so that instead of taking one image, we take thousands of exposures, where in each exposure, only a small number of fluorophores are actually blinking. Now, if you could just imagine it, right? If I have an image and there's only 3 bright dots, then I could localize them. I could just stick a Gaussian everywhere I see a bright dot. And in that way, you get a super resolved image, which is kind of what you see over here. But the difficulty is that now, instead of having one image, we take thousands of exposures. So we could get down to really good spatial resolution of on the order of 20 nanometers, but this is done at the expense of limited temporal resolution. And the difficulty is that we can't use this for live cell imaging. So you could do this, if you freeze the cells or you kill the cells, right? They're not moving. But if you want to do live cell imaging, then you can't use this technique. And our motivation here was really to see if we could reduce the number of exposures we need so that we could do live cell imaging. So how could you do that? At the end, we need everything to blink, otherwise we won't be able to view it. So what we did is we dramatically increased the density of the fluorophores. So instead of making it sparse, we actually made it quite dense. And that way we could take fewer images and still cover everything at the end will be fluorescing. But of course, now we have a harder job in localizing it. So we can't just pinpoint it, but we could still try to use sparse recovery techniques. The image itself is no longer sparse because we have many fluorophores that are fluorescing. But what we looked at was sparsity in the correlation domain. So the nice thing about these fluorophores is that they're blinking in an independent fashion. And therefore, if we look at the correlation of these images, so if we just look at the correlation matrix, kind of by definition, it's going to be diagonal because the fluorophores are fluorescing independently. And so that already gives us one level of sparsity. And then the other level of sparsity that we get is that, sorry, this keeps on jumping, is that the diagonal itself is going to be sparse because, again, not all of the fluorophores are fluorescing at the same time. So basically, we set this up as a sparse recovery in the correlation domain. And that's why we refer to this method as SPARCOM, super resolution correlation microscopy. And this was work done a few years ago with a group of Professor Moti Segev at the Technion. And already we can see that just...
Sorry, we just lost the last 30 seconds or so.
Oh my gosh. Okay, I'm so sorry. I think I'm not sharing anymore.
That's right. See,
yeah. All right, so sorry about that. I kept on going, so did I get through this part?
I would rewind.
Okay, so I doing sparse recovery in the correlation domain, that part we covered, hopefully. Okay, good. So these are the results. So what we're showing here is that we could get 2 orders of magnitude faster. So we use 300 frames instead of 12,000 frames. And we still get better resolution here. You can see a cavity that you don't see in the method behind the Nobel Prize. So, so this idea of using sparsity in the correlation domain turns out to be very effective. So this is still totally optimization based. What are the challenges? Twofold. So one of them is that in order for this to work, there's certain parameters of the optical system that we had to estimate. And in particular, the point spread function, the PSF of the system. And the results really depend on that because basically we do deconvolution with respect to that point spread function. So that is one thing that's quite important. And the other is complexity. Okay, so working with these images, the images can be quite large. and doing the recovery could take some time. So the next natural step was to unfold this, okay? So to have a learned version of SPARCOM. And the nice thing is that, again, it's super simple. We use 10 layers. Again, this is resolution, so we get even better resolution than we had before, but now we don't have to know anything about the optical system. So all we get is the incoming image, and it's basically 10 iterations of the iterative algorithm, so it's also very quick, and we get very good results. So this was in optics. We're now working with the group of Professor Gilad to use this for live cell imaging, and that was really our motivation. So we have first results where we've applied this to live cells, and we were able to see at resolution that they couldn't see before. So that was quite exciting. And the next thing we wanted to do was look at, could we apply this to ultrasound imaging? So ultrasound imaging is another wave-based imaging, and therefore, again, it's limited by diffraction. But of course, in ultrasound, we can't inject fluorophores, or we don't want to inject fluorophores into the body. But instead, what we do is we use this SonoView, which are microbubbles that are FDA approved, and we can inject them into the blood system. And then mathematically, we're basically back to the same problem in optics. So we could use, a very similar method. In this context, we refer to it as SUSHI, sparsity-based ultrasound super resolution hemodynamic imaging, because we're using it to image the blood vessels. And actually, the first time I presented this at an ultrasound conference, someone said that it was a very fishy method. But it is kind of fishy because it gives really, really superb resolution. So this is, of course, real data, and you can see, the blood vessels at resolution that you couldn't see before. So, we've used this for many different ultrasound applications. I'll skip that. Let me just, in the interest of time, I do want to show this. So we've recently done a clinical study with about 20 patients in Beilinson hospitals, together with Dr. Hugo Grubstein, who's leading the radiology at Beilinson Hospital. And these are all breast cancer patients, where the goal was to see if, using these super resolution ideas, we could detect what the tumor is just from ultrasound. And that is very hard to do today. So if you look, for example, at these two images, just focus on the top over here, you'll see that in both of them, you see a lesion. It's kind of like a black hole, but you can't see inside that lesion. And that's why you can't use ultrasound to know what kind of tumor it is. But after using these super resolution ideas, if you look at this image over here on the right, then you see that these two lesions look very different. And here there's blood vessels throughout the lesion, which actually indicates that it's a benign lesion. And here, unfortunately, the blood vessels are only in the periphery over here, and that unfortunately indicates that it's a malignant lesion. So, this was exciting that just by applying this to ultrasound, we could actually use ultrasound to detect the type of lesion without having to go through biopsy and more elaborate testing. So let me just end this part by briefly mentioning these recent ideas that we've been working on with Miguel and his postdoc, Wei Pu. So the nice thing, again, is because we have an optimization framework, we can now think of using various different powers that we have in optimization and getting appropriate networks from them. So one natural thing that was already raised before in questions is looking at robustifying networks. So what happens if we now take, let's say, a robust optimization solver and use that to get an architecture that is robust? So we tried this, for example, again, going back to the standard list on the standard, robust sparse recovery problem. And now I could assume that I want to be robust also to perturbations in the underlying matrix. So I'm no longer going to assume that the underlying matrix is fixed. Now, this is a well-known optimization problem. You could go ahead and solve it, and you can show that from an optimization perspective, this is equivalent to solving this kind of modified least squares problem, where you have this denominator that doesn't appear in the original formulation. And now if you unfold this, obviously you're going to get a different network that also incorporates this denominator. So, that leads to a new form of a network. So the structure of the network is different. It's not just an external metric that we're using. And, lo and behold, when we test this network with different perturbations, then we do see, of course, that it is more robust to other networks that have been proposed for this problem. So I think, this is a really nice example of and relates to the questions that were asked before, that by using this optimization framework, you could now incorporate robustness or other metrics that you want to incorporate it, and it will actually affect the network architecture itself in a way that makes the overall algorithm more robust.
Yonina, can I pick up on that? That fits in beautifully with a question that came up from Chris Anley. Chris says, excellent presentation, thank you. But he has a security question. Do you have any data or references, and perhaps the one you just provided is one of them, about the vulnerability of Unrolled networks to adversarial perturbations or privacy attacks such as membership inference, model inversion, or model stealing?
Yeah, that's a great question. So thank you so much. And I have to say right away, that's something I'd be super happy to follow up offline. So I'd be very happy if whoever, if whoever asked the question would send me an email. I'd love to chat about that more. But let me just give a brief answer here. So that's a really important question, and Miguel and I have been talking about that as well. So yes, we truly do believe that by incorporating these ideas into the optimization problem, we could get networks that are robust to what we incorporate into the optimization problem. And furthermore, again, we could doubly incorporate it. I can incorporate it into the metric that derives my architecture. And of course, I could also incorporate it in the external metric that I'm using for learning. So, we definitely, at least in preliminary tests that we've done, we definitely observe empirically that these methods are more robust to whatever it is I'm trying to be robust against, depending on what I put in the regularization function. And I think proving it is super important. So, and even maybe before proving it, because obviously proving things is hard, but even let's say proving algorithmically. So, doing what would be common tests in that literature to establish, robustness or security, et cetera, I think would be extremely valuable and definitely something I'd be super happy to follow up on.
Awesome. So just checking, doing the kind of robust training that someone like Alex Madry has proposed for regular deep learning, you're suggesting that has not yet been tried in this context, but it would be a really interesting thing to try. So
to try, but also incorporate it into the architecture. So like what Alex Madry is doing, which is beautiful, of course, is external to the architecture, right? It's a metric that you add on to the architecture itself. But here I can also incorporate that in the metric that's deriving the architecture. Okay, so that's what I mean kind of by doubly incorporating. So I can incorporate into the architecture itself and externally in doing the learning, and look at the power of doing that doubly incorporating it into the architecture. And I think that could be really, really powerful, and also maybe give us more insight into that interplay between those two influences.
Fantastic. So thanks again to Chris Hanley, and you are encouraged to follow up with Yonina.
Yes, definitely. Thank you. All right, so I think we're running out of time. Let me just, I could do this in 2 minutes just to give the flavor. And again, anyone interested, I'm happy to refer you to more applications. But this is kind of focusing more on the communication aspect of what we've talked about, which is not unfolding, but more this kind of plug-in approach. So, so just to remind you of the main idea. So, here again, we're going back to our favorite algorithm. And now what we're going to be doing is, instead of using this to develop iterations, we're going to look at the block that depends on something we don't know and replace only that block by something learned, where if we can, we're going to try to do the learning locally. So, that block is going to be learned based on input output data to that block. Again, if we can, sometimes that's not possible. So we'll do the learning end to end. But again, we're not learning all the steps, only the block that we don't actually know. And we've used this in many, many applications. So I've already mentioned the Viterbi net for the Viterbi decoder. We've been doing a lot of work recently together with Neil and other collaborators on using this for Kalman in Kalman net. So for example, instead of replacing the whole Kalman network by a learned network, we're only going to learn the Kalman gain, which incorporates everything about the channel. And in retrospect, that's a super intuitive idea, but people didn't look at that before, and it actually works, not surprisingly, very, very well, but still gives you all the nice advantages of Kalman, the nice implementation. You're just learning the gain itself. So we've used this in many different applications. Let me just kind of highlight maybe one or two. So this is just kind of review of what people did before on simple decoding using deep networks. And there's been a lot of work, but a lot of it has the same flavor of this, end-to-end learning and basically throwing away everything we already know about the networks. On the other hand, if we look at, for example, plugging in to the Viterbi algorithm, we're keeping the Markovian structure, which we know. We're keeping this dynamic programming structure. So no need to get rid of that just because I don't know the actual channel realization. And it turns out that the only place the channel realization appears in the Viterbi decoder is in the likelihood computation. So rather than doing end-to-end learning, we're now only learning the likelihood block. And that's something that's very easy to learn. And then the rest of the Viterbi decoder we're leaving intact. And as you can imagine, it leads to very good performance, which also approaches the optimal performance when the channel doesn't change too much. We could do the same thing for many other methods. So for factor graph methods, again, the same idea. Rather than learning everything end to end, we keep this factor graph interpretation. So this maybe relates to the Bayesian questions. We do message passing over the graph just like you would do before, but we learn the graph nodes. So instead of replacing all of this by a network, we keep all the nice things we know about message passing and only learn the nodes that we need to learn. So, that's very similar in spirit to Viterbi. We've applied this to various different communication applications. And just to mention one last thing, so we could do this also for things that are maybe less principled, like successive interference cancellation. So that's just a greedy method where you find the strongest user, remove them from a channel, and keep on going. And here again, also this we could do in a data-driven method where the difficulty is knowing, who is the strongest receiver and by how much should I remove it. So again, we just learn those components using soft decoding, but keep the overall flow of successive interference the same way as we would before. So all of these are examples where instead of replacing everything by deep network, we're keeping, the nice properties of these underlying algorithms, but only replacing the key components that depend on knowledge that we may not have. So to summarize, we've tried to kind of, present a framework to bridge between these machine learning and deep learning methods with signal processing. Hopefully I've given, various applications to show that this could work well in practice. There's of course many, many open questions. So a lot of good questions that people already asked, a lot of questions on the algorithmic side. And I would say, really a lot of very interesting and open questions on the theory side that, we've begun looking into. Miguel and I are doing a lot of work on that. And maybe I could use this, Miguel, with your permission, to say that we're very happy to recruit more students and postdocs to work on this. So anybody interested, feel free to reach out. And let me just end by saying that we have a recent review that summarizes a lot of this. So you could go ahead and look at the details. And of course, thank my amazing group of students and postdocs that have contributed greatly to this work, and my amazing collaborators who've contributed greatly to this work. And thank you very much for your attention.